Hello students, so in previous class we have studied about the solution of Lagrange's linear differential equation. Okay, so in today's class we'll be studying about solutions of one-dimensional wave and heat equation. You have a derivation related to one-dimensional wave and heat equation, which I'll be explaining in my next video. So in today's class we'll be studying a solution related to one-dimensional heat and wave equation. Okay, so to find the solution of one-dimensional heat and wave equation, we need to obtain a various possible solution. Okay, we need to obtain a various possible solution of ordinary differential equation by taking a constant equal to 0, positive and negative. So let us know about that. Okay, so various possible solution of one-dimensional wave equation. This is an one-dimensional wave equation formula. So just remember this. The derivation of this one-dimensional wave equation will be taught in my next video. So various possible solutions of one-dimensional wave equation utt equal to c square into uxx by the method of separation of a variable. This is very important. Either solution of wave equation or heat equation will be asked. Similarly, derivation of heat or wave equation will be asked. Okay, those questions are extremely important. So first of all, you have utt equal to c square into uxx, right? So can I write utt equal to c square into uxx as dou square u by dou t square, right? Because utt is also equal to dou square u by dou t square equal to c square. I'll write as it is. Uxx can also be written as dou square u by dou x square. Okay, so dou square u by dou t square is equal to c square into dou square u by dou x square. Okay, so here let me consider, let u be equal to capital X into t. Okay, so let u be equal to capital X into t, where capital X is a function of x, capital X of x, and capital T is a function of t. Okay, so let these be the solutions of a partial differential equation. So we need to find the general, finally we need to find what is the capital X and the capital T. That gives you the general solution of a partial differential equation. Okay, so let u be equal to x into capital T. Finally we have to substitute whatever capital X and capital T we find. So that gives you the solution of a partial differential equation, where capital X is the function of x and capital T is the function of t. Alright, so next, hence the partial differential equation becomes, okay, so just to substitute in this question, sorry, whatever you have considered, just replace u is equal to capital X into t. So when you replace u is equal to capital X into t, what do you get? Dou square into capital X into t divided by dou square t square equal to c square into dou square of capital X into t by dou square x square. So with respect to t, which is a constant here, x is a constant, right? With respect to t, x is a constant. So x can be written outside the derivative. Okay, with respect to constant can be kept outside the derivative, partial derivative. Similarly, with respect to x here, which is a constant, t is a constant, right? So I can write it as capital X into dou square t by dou t square equal to c square into, here t is a constant with respect to x, so t into dou square x by dou x square. So partial differential equation assumes an ordinary differential equation of the form, or this can also be written as capital X into a similar way. Capital X is the constant with respect to t. Keep it outside the keep it outside the derivative, not the integral, outside the derivative, sorry. So capital X into d square t by dt square equal to c square into capital T into d square x by dx square. Okay, so what we have to do next is we have to equate both the sides to a common constant k. Before equating it to a common constant k, I do want this capital X and c square t here. Okay, I do want this capital X and capital X, c square and t here. So what am I supposed to do is I have to divide on both the side by c square into x into t. I don't want this constant here, x c square t. So divide on both the side by c square into x t. So when you divide this by c square into x t, what gets cancelled? X and x will get cancelled. What remains in the denominator? C square into t will remain. So you get 1 by c square t into d square t by dt square. Similarly, divide the second term also by c square x into t. So c square c square t will get cancelled. What will remain here? 1 by x into d square x by dx square. So after dividing it, we have to equate both the sides to a common constant k. Okay. After dividing this, we have to equate both the sides to a common constant k. That is 1 by x into d square x by dx square equal to k. First, I need to find capital X. Then I need to find capital T. So I'll write x term first. So 1 by x into d square x by dx square equal to k, and 1 by c square t into d square t by dt square equal to capital K. Now take this x what you have towards the LHS denominator, take it to the RHS. So this x will get multiplied with the k and you get k into x. Similarly, take this c square t, whatever you have in the denominator of LHS, to the RHS. So that will be k into c square into t. Next, what we have to do is we have to bring that kx to the LHS. So that will be d square x by dx square minus k into x is equal to 0. Similarly, bring this kc square t to the LHS. So that will be d square t by dt square minus c square kt equal to 0. Now, this is a differential equation. So, according to differential equation, what is d square by dx square also equal to? D square by dx square is also equal to capital D square, and d square by dt square is also equal to capital D square in a second equation. Okay. So, I'll replace the d square by dx square as capital D square here, and I'll take x as a common term. Here also I'll replace d square by dt square as capital D square, and I'll take t as a common term. So, what you will get? You will get d square minus k into x equal to 0. Here you are taking t as a common and replacing d square by dt square as capital D square. So you get d square minus c square into k into t equal to 0. Okay. Next we have to write its auxiliary equation. So before writing its auxiliary equation, as I mentioned in the beginning, we need to obtain the solution of ordinary differential equation by taking the constant equal to. You have to apply 3 different cases here because you don't know what is the value of k. So you have to find case 1 as k equal to 0. Next you have to find the case 2 as k equal to positive, and next you have to consider case 3 as k equal to negative. Thus we obtain 3 possible solution for the associated partial differential equation. Okay, we obtain 3 possible solutions for the associated partial differential equation. So first of all, let me denote this as equation 1, so that all the cases k equal to whatever you will consider in each case, that you will be substituting in case 1, in equation 1. So case 1, when k equal to 0, let k be equal to 0. So what will happen when you substitute k equal to 0 here? What will happen when you substitute k equal to 0 here? You get d square into x equal to 0. Here also when you substitute k equal to 0, what you get? D square into capital T equal to 0. So d square into x equal to 0 and d square into capital T equal to 0 you will have when you have substitute k equal to 0. So what is its auxiliary equation? So its auxiliary equation becomes, these are the equations when you substitute k equal to 0. So in both the equation, auxiliary equations is m square equal to 0, right? For this also, auxiliary equation is you are replacing d equal to m here. So you get m square equal to 0. For this also you get m square equal to 0. So what is its solution? How do you write its solution? Therefore m is equal to 0, 0, which means that the roots are real and equal. So if the roots are real and equal, so this is for capital X. Therefore capital X will be equal to C1 into C2x into e to the power 0x. Okay, that is the first solution. Capital X is equal to C1 plus C2x into e to the power 0x. If the roots are real and equal, m is 0 here. For the second, t is equal to capital T equal to, there also the roots are the same, m equal to 0, 0, where the roots are real and equal. So C3, C1 and C2 you have already used. So when you are writing for t solution, t will be equal to C3 plus C4 into t e to the power 0 into t. So after writing capital X and capital T, we have to finally write the solution of a partial differential equation. What is the solution of a partial differential equation? It is given by u is equal to capital X into t. Okay, u is equal to capital X into capital T. So substitute whatever capital X and capital T you have obtained. Here e power 0x and e power 0t, it is always equal to 1. So you get capital X is equal to c1 plus c2x and capital T equal to c3 plus c4 into t. So that is your solution of a partial differential equation when constant t is 0. That is when k equal to 0. Next we'll move on to case 2. Case 2, let k be positive. Let k be positive. Say k be equal to plus p square. Okay, let k be positive. Say k equal to plus p square. So where am I supposed to substitute a plus p square now? In equation 1. So when you substitute k equal to p square in equation 1, the equation becomes d square minus, you have k here, so you will be replacing k by p square. So d square minus p square into x equal to 0 and d square minus c square into t square into t equal to 0. Okay, so after substituting k equal to p square, we have to write its auxiliary equation. So what is auxiliary equation of this? It is m square minus p square equal to 0 is auxiliary equation of the first term, and of the second term it is m square minus c square into p square equal to 0. Okay, so take minus p square to the other side, you get m square equal to p square, or m is equal to plus or minus p. Similarly, take minus c square p square to the other side, you get plus c square p square. Therefore, m is equal to plus or minus c into p. So, what kind of roots are these? M equal to plus or minus p is for x, and m is equal to plus or minus cp you got for the function t. Alright. So, what kind of roots are these? These are one pair of complex root, right? Compare it with the alpha plus or minus I beta. So what do you have in the place of alpha? In the place of alpha, sorry, it is not one pair of complex root. It is a real and a distinct root. Okay, plus or minus p means it is plus p comma minus p. Here also plus or minus cp means plus cp comma minus cp. So you have a real and a distinct root. So how do you write its solution whenever you have a real and distinct root? For this it is x is equal to, you write capital X is equal to C1 into e to the power. C1, C2, C3, C4 you have already used. So you can use the next term, that is C1 dash, C2 dash, C3 dash, C4 dash. Here I have written C1, C2, C3, C4 only. But when you are writing the solution of a partial differential equation, you are not supposed to write it as C1, C2, C3, C4. You have to write it as C1 dash, C2 dash, C3 dash, C4 dash. Okay. So your x is equal to c1 dash into e to the power p1 px plus c2 dash into e to the power minus px, and capital T is equal to c3 dash into e to the power cpt plus c4 into e to the power minus cpt. So what you have to do is, here is you have to just replace m is equal to m1 and m2 by plus p and minus p. Here you have to replace m1 and m2 by plus cp and minus cp. Okay, therefore the the solution of a partial differential equation when constant is positive is given by u equal to x into t, where x is equal to c1 dash into e to the power px plus c2 dash into e to the power minus px into c3 dash into e to the power cpt plus c4 dash into e to the power minus cpt. It's better you write here also c1 dash, c2 dash, c3 dash, c4 dash, so you will not have a confusion, because c1, c2, c3, c4 is already being used. Now let us move on to the last case now. Let k be negative. Say k is equal to minus p square. Let k be negative. Say k is equal to minus p square. So when I substitute k equal to minus p square in equation 1, then minus into minus will be plus there. So you get d square plus p square into x equal to 0, and d square minus into minus will be plus c square. Minus into minus equal to plus c square into p square into t equal to 0. So the equation becomes d square plus p square into x equal to 0, and d square plus c square p square into t equal to 0. Okay. So next we'll write its auxiliary equation. So what are the auxiliary equation? M square plus p square equal to 0, and m square plus c square into p square equal to 0. So I'll take a plus p square to the other side. Here also I'll take plus c square into p square to the RHS. So when you take plus p square to the RHS, you get m square equal to minus p square. And similarly, when you take plus c square into p square to the RHS, you will get minus c square into p square. So what is m? M is equal to plus or minus square root of minus p square, which is equal to I into p. Similarly, m is equal to, for the second one, m is equal to, you get plus or minus I into Cp. Okay, so what is this is you have I into P here. Here also you have I into Cp. So these are one pair of complex roots. So what is alpha here? Alpha is 0 on in both the term, whereas beta is P for the first term, whereas beta is equal to Cp for the second term. Therefore, it's a solution R. This is the solution for x. Therefore, x is equal to, here also I have written C1, C2. You please change it to C1 double dash cos Px. Okay, you're changing beta to P. Okay, it's not, I mean, it's not wrong if you write C1, C2, C3, C4 when you're writing a solution, but make sure when you're writing the solution of a partial differential equation, C1, C2, C3, C4 has been replaced by some other constant. Okay, so capital X is equal to C1 into cos Px plus C2 into sin Px. Beta alpha is 0, so e to the power 0 into x will be equal to 1. And the solution for capital T is C3 into cos, beta is Cp here. So cos beta Cpt plus C4 sin Cpt. Hence the general solution, solution of a partial differential equation when constant is negative is given by u is equal to x into t. So what I have done here while writing the solution of a partial differential equation is I have replaced C1, C2, C3, C4 by C1 double dash, C2 double dash, C3 double dash, C4 double dash. Write the final solution of a partial differential equation. Okay. So this is the solution of wave equation. So next we will move on to find the various possible solution of one-dimensional heat equation by the method of separation of variables. It's exactly similar to wave equation, but instead of UTT you will have a UT. Okay. So the derivation of heat equation also will be taught in the next video. Okay. So in today's class we'll study the solution of a one-dimensional heat equation. So this is an one-dimensional heat equation. Ut is equal to c square into uxx. So ut can also be written as dou u by dou t, and uxx can also be written as dou square u by dou x square. All right. So let me consider dou u by dou t is equal to c square into dou square u by dou x square. So what am I supposed to do next? Let u be equal to capital X into t. This is exactly similar to the solution of one-dimensional heat equation. The only changes you have here is in the equation. You have utt there, and here you have just a ut. Then rest everything is exactly same. So if you study just wave equation, it is sufficient because heat equation is exactly similar to that. Alright. So let u be equal to capital X into t. Let u be equal to capital X into t, where capital X is equal to function of x and capital T is equal to function of t, be the solution of a partial differential equation. Okay, let these be solution of a partial differential equation. Hence the partial differential equation becomes, so just to substitute u in the LHS as well as in the RHS as capital X into t. So you get dou of capital X into t by dou t is equal to c square into dou square of capital X into t by dou x square. Okay, so towards LHS as well as towards RHS, just replace wherever you have capital, wherever you have u, just replace it as a capital X into t. So dou of capital xt by dou t is equal to c square into dou square of capital X into t by dou x square. Alright, so again you see here with respect to t, capital X is a constant. So keep constant x outside the partial derivative, and here also the capital T is a constant with respect to x. So keep capital T outside the partial derivative. Keep capital T outside the partial derivative. So what do you get here now? And the next step, capital X into the partial differential equation changes into ordinary differential equation. Capital X into dt by d capital T by dt is equal to c square t into d square x by dx square. capital x is equal to dt by dt is equal to c square into t d square x by dx square. So I don't want this x and c square t here. So what will I do is I'll divide on both the side by x into c square t. I'll divide on both the sides by x into c square into t. So when you divide this by c square into t, c square x into t, x and x will get cancelled. You get 1 by c square into t dt by dt is equal to, here also when you divide this by 1 by c square t into x, you get 1 by x into d square x by dx square. Alright. So now you have to equate each term to a constant k. LHS also you have to equate to a constant k. Similarly, you have to equate even RHS also to constant k. So equating both sides to a constant k, we get 1 by c square t dt by dt is equal to k, and 1 by x into d square x by dx square is equal to capital K. K. So now what we have to do next is we have to take this c square t, whatever you have in the LHS denominator, to the RHS. So you get dt by dt is equal to k into c square t. Here also d square x by dx square is equal to k into capital X. Okay. So that is what I have done in the next step, and I have brought both the term to the LHS. So plus the c square kt, whatever you have in the LHS, when you bring it to the RHS, that will be dt by dt minus c square into kt equal to 0. And here also when you bring the k into x to the LHS, it will be minus k into x equal to 0. So next we know that d by dt is equal to capital D, and d by dx square d by dx is equal to capital D. Okay, d by dt means it is also equal to capital D, and d by dx means it is equal to capital D, but d square by dx square means that is equal to capital D square. So what will this first term be? Capital dt minus c square kt equal to 0. But between these two, which is a common term? When you replace d by dt by capital D, t is a common term. So take a t as a common outside. So you get d minus c square k into t equal to 0. Whereas for the second term, when you replace the d square by dx square by capital D square, so capital D square x minus k into x equal to 0. Take x as a common term. So you get d square minus k into x equal to 0. Okay. Next, write its auxiliary equation. So what are the auxiliary equations of this? This is my equation 1. So auxiliary equations are, So before writing the auxiliary equation, what are we supposed to find here now? We have to find the solutions, right? We have to find the solution of we have to find the solution of a partial differential equation. So here we don't know what is the value of k here. So we'll use we'll consider 3 cases for the to find the values of k. Okay. To obtain the solution of a associated partial differential equation. So first of all, case 1, when k equal to, let k be equal to 0. So when you substitute k equal to 0, what you get in equation 1? When you substitute k equal to 0, you get capital D into m equal to 0. Here also when you substitute k equal to 0, you get a capital D square equal to 0, right? You get capital D square equal to 0. So for the first one, the auxiliary equation is m equal to 0. Since when you substitute k equal to 0, you get capital D equal to 0. So its auxiliary equation is m equal to 0. For the next one, what do you get? You get m square equal to 0. Since you have d square equal to 0 there, you get your auxiliary equation as m square equal to 0. So what is m is equal to? M is equal to 0 for the first one, and for the second one m is equal to 0, 0 are the roots. So how do you write its solution now? Therefore the solution this is for t now. So t is equal to, you have only one root 0. So c1 into e to the power 0t. So e to the power 0t means it is equal to c1. So c1 into 1 is equal to c1. Whereas for the second one you have real and equal roots. M is equal to 0, 0 are the roots. So therefore capital X is equal to c1 plus e2x into e to the power 0 into x. Okay. C1 you have already written, so that will be c2 plus e3x into e to the power 0x. Okay. E to the power 0x means that is equal to 1. So you get c2 plus c3 into x. Here it is written c2 x plus c3. No problem. That is also right. After writing its solution of ordinary differential equation, we have to write the solution of a partial differential equation. How do we write it as? We know that u is equal to x into t. So just substitute what is x and what is t. So x is c2 plus c3 into x, and t is c1. So you get c1 into C2 plus the C3 into x. That is the solution of a partial differential equation when k is constant is 0. Next, let us move on to case 2. Okay. So let k be positive. Say k is equal to plus p square. So when you substitute k is equal to plus p square, what do you get? The first term as you get m minus c square p square equal to 0, and the second one auxiliary equation you obtain is m square minus p square equal to 0. So here you take minus c square p square to the LHS, so you get m is equal to c square p square. When you take minus p square to the other side, you will get m is equal to plus or minus p. Here you have only one pair of root, and here you have real and a distinct root. So how do you write its solution? Therefore, t is equal to, see here, c1 dash I've used because c1, c2, c3 is already used. You can use c4, c5, c6 also, no problem. So c1 dash into e to the power m into t. This is for t now. Okay, so m you have to replace it by c square p square. So c1 dash into e to the power c square p square into t, and this is for x and it is real and distinct. Therefore, x is equal to c2 dash into e to the power px plus c3 dash into e to the power minus px. You are replacing m1 by p and m2 by minus p. Okay. Then finally you have to write the solution of a partial differential equation, which is u is equal to capital X into t is equal to c1 dash into e to the power c square p square into t into c2 dash e to the power px plus c3 dash into e to the power minus px. So these are the solutions of a partial differential equation. Next is case 3. Let k be negative. See, k is equal to minus p square. So let k be negative. So when you substitute k equal to minus p square, what do you get? Minus into minus will be plus. So your auxiliary equations are m plus c square p square equal to 0, and m square minus into minus will be plus p square equal to 0. Take a plus p c square p square to the RHS. You get m is equal to minus c square p square. Similarly, take this plus p square to the RHS. You get m square equal to plus or minus the square root. You get m square equal to minus p square. Therefore, m is equal to plus or minus I into p. Here you have one root minus c square p square, whereas the second one is one pair of complex root where alpha is 0 and beta is p. So write its solution. T is equal to c1 double dash into e to the power minus c square p square into t, and here x is equal to alpha is 0, so you need not write that. Anything to the power 0 is 1, so c2 double dash into cos of beta is p, so cos px plus c3 double dash into sin px. Finally, write it's a partial differential equation. Solution of a partial differential equation when k is a negative or when constant is negative is u is equal to x into t. So this is t and this is x. Okay. So these are the three solutions of heat and wave equation by the method of variable separable. Thank you.